two methods is that in the Adamian decomposition method, we consider the function u0 of x equals the non-homogeneous part of the integral equation, I mean f of x, and construct the recurrence relation using the formula un plus 1 equals lambda times the integral of k u n and the n, actually n that satisfies this recurrence formula is greater than or less or equal to 0. But in the modified decomposition method, we are supposed to have a function f such that f can be written as a summation of two separate parts, f0 and f1. And in this method, we suppose that u0 is f0, u1 is f1 plus lambda, the integral of k u0. I don't write the part dt and also the bounds of the integration for simplicity. And the recurrence formula is similar to Adamian decomposition method. I mean un plus 1 equals lambda times the integral of k un. So the only difference between these two methods is that in the modified decomposition method, we suppose that the function f, which actually makes the non-homogeneous part, can be written in the form of summation of two different functions, f0 and f1. And we suppose that u0 is f0, u1 is the summation of f1 and the integral part that is dependent to the value of u0, and the recurrence formula is completely similar to Adamian decomposition method. If you remember, we had in some cases, in some examples, the actually property that some terms with actually opposite signs appear in the summation. For example, in u0, u1, and the other terms, we had similar terms with opposite signs. For example, we had sine of x plus 2 times x as u0, but in u1 we had negative 2 times x. And these 2 times x and these 2 times x can be deleted. We call this phenomenon as the noise terms phenomenon. So we want to discuss about this phenomenon and to check that when this phenomenon happens. The noise terms, as I said, are similar expressions or terms with opposite signs. And since we can delete similar expressions with opposite signs, so we call them noise terms. For example, here in example 8, we have the integral equation u of x equals x cosine of x plus 2 times x plus the integral of x times u from 0 to pi. If we use the Adamian decomposition method, we have this part as u0 because this is f0, and also we can have our recurrence formula using this initial value. So u naught of x equals x times cosine of x plus 2 times x, which is the part f of x. And for the other terms, we have this recurrence formula that uk plus 1 of x equals the integral of x uk of t dt from 0 to pi. If we use this recurrence formula for obtaining the function u1 of x, we will have u1 of x equals negative 2x plus pi squared times x. If you pay attention, in the function u0 and in the function u1, the term 2 times x can be seen with opposite signs. In this term, we have positive sign for 2 times x, and here we have negative sign for 2 times x. And if we add these two functions as the two first functions in the series of the function u of x, it can be seen that this expression and this expression are deleted. So here the noise terms positive, negative 2 times x appear in u0 of x and u1 of x. Cancelling this term from the zeros component u0 gives the exact solution. If you continue the process, actually, if you compute u2 of x using the recurrence formula, the integral of 0 to pi x u1 of t, which is negative 2 times t plus pi over 2 times x times t dt, then the result will be somehow that the term pi squared times x appears with negative signs. So we have the other terms, somehow all expressions can be deleted from this summation, and just the expression x times cosine of x remains as the solution of our integral equation. Is it clear? Did you understand? Okay. In the next example, also we can see the phenomenon of noise terms. We want to solve this integral equation using the Adomian method. So we have the non-homogeneous part as u0 of x, and using the recurrence formula, we can obtain the function u1 of x as you can see here. If you pay attention to the terms that we have in our function u1 of x and compare them with the terms that we have in the function u0 of x, you can see that this expression, I mean 2 times x minus pi over 2 times x, and this expression negative 2 times x plus pi over 2x are actually with opposite signs. So the noise terms negative positive pi over 2 times x and negative positive 2 times x appear in u0 of x and u1 of x. So we call this term with positive and negative sign and this term with also negative and positive signs as noise terms. So by deleting these noise terms and by continuing the process and having the other terms of the function u1 of x as noise terms, we can see that the solution of this integral equation is u of x equals cosine of x minus sine of x. Let's consider the next example, example 10. Once again, we have Fredholm integral equation and we want to study on the noise terms. We have the non-homogeneous part, f of x. We set u0 of x equals f of x, and also we have this recurrence formula for computing the values of uk plus 1 for all k greater than or equal to 0. So using the initial value of u0 and using the recurrence formula, we can obtain the value of u1 of x as you can see here. If you pay attention, you have pi over 2 times x here with positive signs and here with negative sign. And also you have x with negative sign and x with positive sign. So these two terms appear with opposite signs in u0 and u1. So we call positive, negative pi over 2 and pi over 2 times x and positive, negative x as noise terms. So we obtain u of x equals x times tangent inverse of x. If there is any question, you can ask. Yeah. Okay, let's continue. Here we want to discuss about the variational iteration method. In some articles or books, you can see the abbreviation VIM. So it means variational iteration method. This is the abbreviation of this expression. In this section, we want to discuss about variational iteration method, or as I said, VIM. that was used recently in the literature to handle both differential and integral equations. So this method can be used for solving differential equation and also integral equations in both kinds of linear and nonlinear cases. In Adamian decomposition method, you saw that we have the components of the decomposition series by using a recurrence relation. But in the variational iteration method, we have successive approximations of the solution. I mean, for example, we make the solution somehow. We don't have series of ui or un as the function u, that u is our solution of the integral equation. Here we make actually a successive relation that, for example, un plus 1 can be written using un, but we have limit of un when n approaches infinity equals u, which is the solution of integral equation. So the difference between variational iteration method and in Adamian decomposition method is that in Adamian decomposition method, we have a series summation of ua as the solution of integral equation, but here we have the limit of a sequence un as the solution of the integral equation. Now we want to explain about this method and to see that how we can use it for solving Fredholm integral equation. This method works very well if the kernel K is separable of the form g of x times h of t. So we have considered this special case that the kernel K can be written as a separable function. Here you have the function g just in terms of x, and you have the function h just in terms of t. So we consider this special case, and we want to apply variational iteration method for solving the Fredholm integral equations with this kind of kernels. The Fredholm integral equation by this way can be converted to an identical Fredholm integral differential equation by differentiating both sides. So first of all, we take derivative from both sides of the integral equation of this form, and then transform it to an integral differential equation, and then apply the variational iteration method for solving the resulted equation, I mean this equation. For simplicity, first we will study only the cases where in our separable function k, kernel k, form of g of x is given by x to the power n. So, because when the form of this function is different, the method is applied in a different way. We just consider this case, and for introducing the method, we apply it for special cases when we have g of x equals x to the power n for n greater than or equal to 1. So consider that we have this Fredholm integral equation, or if we suppose that the function k is written as g of x times h of t, you know that this function is independent with respect to the integral, actually direction t, and can be taken out from the integral sign. So we have an equivalent form for this Fredholm integral equation, as we can see here. U of x equals f of x plus this g is written outside of the integral, so we have the multiplication of g times the integral of h u dt, by supposing that k of x and t is the multiplication of g of x and h of t. And as you see, this integral only depends on t. We don't have any x here. So it is equivalent to a constant, because when you take integral and replace the lower and upper bound, you will obtain a constant for this integral part. First of all, by taking derivative from both sides of this equation with respect to the variable x, we have in the left side u prime of x, and in the right side we have f prime of x plus g prime of x times, since it is a constant, it will remain unchanged. So we have g prime of x times this integral. So this is the resulted integral differential equation, and we want to apply the variational iteration method for solving this. And you know that when two equations, this equation and this equation, are equivalent, their solution is same. I mean, when you solve this equation, you somehow obtain the solution of this main equation. In the variational iteration method, we have the recurrence formula as you see here. We have un plus 1 of x equals un of x plus the integral of lambda of kc. We will explain about these parameters, times un prime of kc minus f prime of kc minus g prime of kc times this integral. If you compare this part in the parentheses, you can see that this is exactly this integral differential equation when we take the right hand side to the left hand side. Here you have u prime of x minus f prime of x minus g prime of x times this integral equals 0. So you can see this expression in the parentheses exactly. So here lambda is a general Lagrange multiplier. We call it actually Lagrange multiplier. Lagrange multiplier method is a well-known method. Yeah, Mr. Mohammed. Yeah. Here Yeah, the recurrence formula, actually it is not an integral equation, because in integral equation you have the unknown function in the left and right side similar, but you don't have it similar. Yeah, this is just a form, the variational form of this integral differential equation. But the integral differential equation that we are trying to solve is Fredholm kind, okay? This is the formula of a variational iteration method for this integral equation. You have to remember it for applying it, okay? I was saying that Lagrange multiplier method is a very well-known method in numerical analysis, and you can study about it when you search this expression, Lagrange multiplier method. It can be used for many problems, for example, optimal control problem, or for example, for solving actually systems of equations with some constraint, and many other problems. Note that the Lagrange multiplier lambda may be a constant, so it can be a constant number, or a function of psi. So it can be constant or a function. And un tilde that we used it here, un tilde is a restricted value. That means it behaves as a constant. So we have the change of un tilde equal 0. This notation delta means the change of the function un tilde. So delta of un tilde means increment or change of function un tilde. And it explained it here. Delta is the variational derivative. The Lagrange multiplier lambda can be identified optimally via the variational theory as proved in the literature. So after you applied this method, you can find the value of lambda. You can recognize it using the theorems about the actually optimality condition in some books. The variational iteration method depends mainly on two essential steps. First of all, we should determine the Lagrange multiplier lambda that can be identified optimally via the variational theory, where integration by parts should be used for finding it. As I stated before, lambda may be a constant or a function. After actually considering this condition, you can find it and recognize if it is a constant, whether it is a constant or a function. And it is different from one question to another. It means that if you consider two different Fredholm integral equations, you will obtain two different lambda when you apply variational iteration method. So this lambda is not a fixed function or a fixed constant. It depends directly to the problem that you are trying to solve. If the integral equation is different, so the function lambda will be different as well. Here, for our present use, for solving or applying the variational iteration method for solving Fredholm integral equation, we consider lambda of psi equals -1 for first order integral differential equations. So here, for the sake of simplicity, you can suppose that lambda is -1. When you have the value of lambda, the iteration formula without this restricted variation can be given as, here you can compare that, this equation and this equation, and find that only the value of -1 instead of lambda has been replaced in this equation. So here you have un plus 1 of x equals un of x minus, because we replaced -1 instead of lambda, minus the integral of variational part from 0 to x. When you have a recurrence formula, you have to consider an initial function u0. This u0 is completely arbitrary, and you can consider it by actually having an integral equation. You can recognize which function instead of u0 can be helpful more. So we will consider different cases of u0 in the next parts. So let me bring the right slide here. We consider this variational problem to determine the successive approximations of un plus 1 of x for n greater than or equal to 0 for the solution u. Notice that un of x gives the successive approximations of the solution and not the components as in the series. So, as I said, the difference between Adamian method and the variational iteration method is that here we have the series of un, but here we have the limit of un that you can see here. So the zeros approximation u0 can be any selective function. So it's completely arbitrary. It depends on you. For example, one of you can choose one u0 and another one can choose another u0. However, using the given initial value u of 0 is preferably used for the selective zeros approximation u0. It means that you have, for example, let me bring the main problem here. You have u of 0 equals f of 0 plus the integral of this actually separable form can be replaced instead of k u t dt. So in most cases the value of u of 0 is given and you can consider it as initial guess or u0. And as I said for many times, we have the solution of the integral equation as the limit of un of x when n approaches infinity. The determination of the Lagrange multiplier is very important in applying this method, I mean variational iteration method. Here we see some cases, or actually the some iteration formula that show ordinary differential equation are seen here, and the corresponding Lagrange multiplier for this kind of ordinary differential equation can be seen in each differential equation. For example, for case I, for the first case, when you have u prime plus f of u of psi and u prime of psi equals 0, this is the differential equation. For this integral equation, value of lambda is given by -1, and the variational iteration method can be given by this formula. For this second order differential equation, the value of lambda is psi minus x. So this is a bivariate function in terms of psi and x. And the recurrence formula using this lambda can be given by this formula. Also, you have to remember these cases, okay? These are not something that you have to obtain the process. Just remember this is actually 5 special cases. So here, what you have to do is to remember each differential equation and the value of lambda that is used for differential equation. This is actually especially thing to do. Okay, just remember the formula of differential equation and also the value of lambda corresponding to that ordinary differential equation. And you can see the other cases of differential equations, and generally when you have a differential equation of order n, you can consider the function lambda as you can see here. This last case actually includes all the previous cases. Yeah, because when you consider the derivative order 4, you have case 4. If you consider the derivative order 3, you have case 3. And for derivative order 2 and 1, you have the 2 previous ones. So, generally, you can say that the value of lambda for an ordinary differential equation of order n can be given by this general formula. When n changes, this lambda also changes. And the variation iteration formula is given by this way. Here we consider some examples to actually understand this actually method better, okay? I was explaining for your friends because I stopped the recorder that you missed 1 month and we have to continue the lecture for today because you don't have any time or many time to waste actually. Okay, so consider example 1. We want to apply the variational iteration method for solving this Fredholm integral equation. Using the process, you know that here actually the kernel is x. You can see it easily. And since it is independent of t, you can take it out from the integral sign, okay? So the kernel k was written as g of x times, let me active the recorder, I forgot to active it. You have actually the kernel k equals g of x times h of t. Can you tell me what the relation of g of x is here? G of x is equal to x exactly, and h of t? H of t? No, is 1. Yes, thank you. H of t is 1 because this part that includes u is always in the integral part, okay? So we have this integral equation. We have a separable kernel k, and the part g is given by x, and the part h is given by 1. As it was explained in the process of the method, first of all, we have to take derivative from this formula. So in the left side, we have u prime of x, and in the right side, we have x times e to the power x plus e to the power x minus 1 plus, here, when you take derivative from the last part, you know that this is the coefficient of x, and the derivative is just this coefficient. So we have the integral of 0 to 1 u of t dt, and we consider u of 0 equals 0. If you consider this actually integral differential equation and use the general formula, this formula, for the variational iteration method, you have, actually you have to consider this relation because we suppose that the value of lambda is negative 1. You have un plus 1 equals un minus, here you have in the parentheses the left side minus the right side expression. So you have un prime of k psi minus k psi e to the power k psi minus e to the power k psi. Just the variable changes because you have the integral of this expression. So we change the variable of integration with respect to the upper bound of the integral. So here we have negative or minus the integral of un of r dr from 0 to 1. So this is the variational form of this integral equation. It is preferable, we have to choose a function for u0 of x, and as I said, it's completely depends on you. You can choose any initial value for u0 of x. Here we suppose that u0 of x is 0. Please make it correct. It's not correct. The value of 1 is not correct. U of 0 was supposed to be 0. So make this 1 0. Okay? It's not correct. Yeah. Delete this one and make it 0. It's not correct. Using this selection into the correction functional, this is the correction functional, gives the following successive approximations. First of all, we have u0 of x equals 0, as we supposed. u1 is given by this formula when we have u0 in the right side, so we have u0 minus the integral of u0 prime minus this function minus this integral. Here you have u0 as 0, so you have 0. Here you have 0. You just need to compute this integral. You also have 0 here because u0 is 0, its derivative is 0 as well. So by computing this integral, you have x times e to the power x minus x. This is the function u1. Let's go to computing the function u sub 2 of x. Using the recurrence formula, we have u2 of x equals u1 minus this integral part. We replace, instead of u1, whenever we have u1, we replace this relation and obtain the result as x times e to the power x minus 1 over 2 times x. If we continue the process, we can see that un of x equals x e to the power x minus 1 over 2 to the power n minus 1 times x. We said that the solution of integral equation using variational iteration method is obtained using taking limits from un when n actually approaches infinity. So we have u of x equals limit of un of x when n approaches infinity. If you compute the limit of this function when n approaches infinity, you know that this part approaches 0. So only this part remains, and we have the solution of integral equation equals x times e to the power x. Correct? Do you understand? Or?
Yes, yes.
Yeah. Let me tell you that the important thing here is to remember that lambda is always -1, and also you have to obtain derivative of both sides of the integral equation. Okay? The next example, to make this method more clear, we have this integral equation. So we have to compute the derivative of both sides. In the left side, we have u prime of x. In the right side, if we take derivative, we have negative sine of x minus 1 plus the integral of u of t dt from 0 to pi over 2. And with initial condition that u of 0 is 1. Here, for obtaining the value of u of 0, you just need to replace 0 here. So you have cosine of 0, which is 1, minus 0 plus 0. Yeah, so the value of u of 0 is 1. The correction functional for this equation is simply given by this formula here. We have the subtraction of left side and right side. We have u prime n plus sine plus 1 minus this integral. We have the initial condition as u of 0 equals 1. So, as we suggested, we can consider u naught of x equals u of 0, which is 1. I don't know why it makes this mistake. Here you have 1, okay? Please make it correct. So, we have u0 equals 1. u1 is obtained using this recurrence formula by replacing u0 equals 1. So we have u0 of x minus this integral part, and we obtain cosine of x minus x plus pi over 2x. For u2 of x, we obtain this function. For u3 of x, we obtain this function. And if we continue the process, you can see the actually general form of these functions. And if you pay attention, for example, in u3 of x, you have this x with negative and positive sign. This expression with negative and positive sign. This expression also with negative and positive sign. And you can see easily the deleting similar terms with opposite signs, and only the term cosine of x remains. So for un of x, we have the same thing, and we can say that limit of un when n approaches infinity is cosine of x. And this is the solution of this integral equation. Do you have any question? Okay, let's continue. The next example, here you can see that we can take this x out of this integral. If we take derivative from both sides, we have u prime of x equals 2 times x minus 1 over 3 plus the integral of 0 to 1 ut dt. Can you tell me the initial value u of 0? Why 1? You just need to replace instead of x 0. Okay, so you have u of 0 equals here, for the first term you have 0 if you replace 0. Okay, the second part will be 0 as well, and the third part, since we have this x as a actually coefficient of this integral part, we have 0 times one expression, so it's not important that expression which 0, exactly, thank you. So the initial value is 0. So we have u prime of x, as I said, in this form, and the initial value is given by 0. The correction functional for this equation using the variational iteration method is this equation. You can see that we take all of this expression in the left side, we change the signs, and we have this equation. Once again, we use the recurrence formula by supposing that u0 of x is u of 0, which is 0. So u0 of x is 0. u1 of x is given by x squared minus 1 over 3x. And if we continue this process, we have the general form of un equals x to the power 2 minus, here you can compare this formula with the with u2 and u3. You have here 1 over 3 times 1 over 2x for the second part. Here you have 1 over 3 times 1 over 2 to the power 2x. So if you compare these two with the general form, you obtain x squared minus 1 over 3 times 1 over 2 to the power n minus 1 times x. And un is the u actually, now let me clear. U is the limit of un when n approaches infinity. If you compute the limit of this function, you can see that the second part approaches 0 and only x squared remains. So we have x squared as the solution of the integral equation given in this example. Okay, since the discussion changed from the next section, I feel it's better to have this discussion for the next lecture. And for today, I think variation iteration method is enough because, because I think it takes a little time to understand it better and solve the exercises of the end of section 2.3. Okay, you have the exercises of variation iteration method part. You can solve them and be expert in this method, because in many discussions, for example, ordinary differential equation, variational iteration, partial differential equation, you can use variational iteration method. It's very effective, but there are two important things: choosing the value of lambda. These two issues are very important: the value of lambda for each problem, and also the initial condition or initial function u0 of x. So, okay, these two issues are very important in variation iteration. Okay, is there any question?
No, دكتورة, thank you.
You're welcome.
No, دكتورة.
Okay, no question. Please study well, because I think comparing to Adomian decomposition method, variational iteration method is a little more difficult, and it takes a little time to understand it better. Please study well and solve the exercises of the exercises in the end of this section, exercises of section 2-3. 2.3 is very important. Okay, have a good day. Goodbye, everyone.
Goodbye.
Thank you. Thank you. Bye.
Thank you.
Bye.
Bye.
Bye.